Hello, everyone. Today we're going to be going through a quick couple examples of how you can use IR spectroscopy to really solve some real chemical problems. So again, as a quick review, there's going to be two major ways we can use our IR spectroscopy. So first, we can go ahead and use our spectra to identify any functional groups that may be present in a molecule. This will go a long way, especially when paired with NMR, to try and determine the true chemical structure of an unknown species. But perhaps one of the most common ones is we can go ahead and verify whether or not we have a compound present in a mixture or in any desired product. This can often be seen as more of the skills of trying to match a spectrum with the molecule of interest. And again, when doing this, big thing you should always have on hand is going to be your full table of all of the various peaks and the bonds that they go with. So let's go ahead and dive right on in. So let's go ahead and say that I know that I have a C5 molecule with 1 oxygen and 10 hydrogens. I'm trying to figure out what the molecule is by IR spectroscopy. So the first useful thing we can do is determine our degrees of unsaturation. So if I've got 5 carbons, the maximum number of hydrogens would be 12. Too short, that means I've got 1 degree of unsaturation. So in here somewhere, I've either got a double bond or a ring. So let's go ahead and try and figure out where it is. So as I go through my spectra, I'm going to start by looking in this double bond region, and I don't have a ton, but I do have one moderate sized peak around 1600. So not quite in about the 1700 region. That's where we have this small impurity over here. But I've got a solid carbon-carbon double bond. Now I need to try and figure out what that is. So let's go ahead and take a look at that hydrogen, the hydrogen region. And lo and behold, I have a nice peak around 3100. That agrees very well with the hydrogen attached to a carbon-carbon bond. So my degree of unsaturation is due to the presence of an alkene. But what on earth is my oxygen doing? So I've got 2 major options from what my oxygen can be doing in this case. So either it can be really attached to an alcohol, or it can just be as part of an ether. So for that, I'm going to go ahead and look to see if I can identify an alcohol. And lo and behold, I have a peak around 3700, decently broad, decent intensity. So that's going to be my OH bond. And we can go ahead and indeed confirm that I do have a CO bond, because I do have a decent peak around 1100, which would agree again with an alcohol. But that said, it would also be present for the ether. So really what I'm looking for is the presence or absence of that OH group to decide in between an alcohol or an ether. So we don't know any information about where these bonds are in conjunction with each other, but it does turn out that this is that this structure is due to 3-pentene-ol. So again, we've got an alcohol, we have an alkene, and so that's our structure. So let's go ahead and do another quick one. Same basic molecular formula, C5H10O. So again, I've got 1 degree of unsaturation. So let's go ahead and take a look. Here, first thing we can go ahead and notice is we have a big swamping peak around 1750. So right there in between 15 and 2000. So that's going to be an easy call here. I've got a carbonyl. So that accounts for both my oxygen and my double bond. Now the question is, what is this carbonyl doing? Do I have an aldehyde? Do I have a ketone? Probably, again, based on formula, I don't have an ester or a carboxylic acid. So for here, I've got to, again, look at those hydrogen peaks. If I've got something to look for whether I have an aldehyde. And lo and behold, I do have my aldehyde fangs, 2 peaks in that 2800 region. So I do indeed have an aldehyde. And this is one of those few cases we can tell the exact structure. It's pentaldehyde, because the aldehyde has to be on the end. And again, note, nothing really going on in the double bonded region. no corresponding hydrogen peaks for double bond. This is a fairly nice, clean spectra, nothing unexpected. So these are classic ways where you can look at a molecule, get a good idea of what it is just based on the functional groups. Now, let's go ahead and try and do a classic problem. Is I have a product mixture, and it's one of, and my spectra could be due to one of three possible compounds. So I could have generated an ester, an carboxylic acid, or I could have a aldehyde. An aldehyde paired with a ester. So this one's going to be a little bit tricky. So we look at our spectra. First thing that I'm going to go ahead and identify is, lo and behold, I do have a carbonyl. However, this doesn't help me a lot because all three of these molecules do indeed contain that carbonyl. Not a lot of help. And indeed, all three of them will contain a CO bond, which is located somewhere in here. Again, not a big help. Which means what I have to go ahead and do is identify what the key coordinations of each of these molecules will be. So if I have my carboxylic acid, I'd expect to see a gigantic peak around 3,300. Not there, don't have a carboxylic acid. All right, well, I could have had an aldehyde. Well, we go ahead and look over in the aldehyde region. I'd expect to see these aldehyde fangs. There's a little something there, but again, not nearly strong enough to really indicate an aldehyde. So that leaves me one option. And this is an important idea, is that sometimes you can identify a molecule not based on the presence of peaks, but instead on the absence. And this is a problem when dealing with ketones and esters, is they tend not to have a lot of big distinguishing features besides that carbonyl coordination. And so that's an important thing to remember when using spectra. Sometimes it's not what is there, it's what's not there. Now let's go ahead and do one last quick problem. So let's say I have a reaction that I want to go ahead and verify. So I want to go ahead and synthesize aspirin. So this is acetyl salicylic acid. So this is molecule here on the right. You can synthesize it from salicylic acid. So the question here is, does this IR spectra agree with the product of methyls of acetyl salicylic acid? All right, so let's go ahead and keep an eye on the big features of this molecule. So indeed, I do have a carbonyl around 1750. I do indeed have a decent aromatic region, as can be seen with the hydrogen peaks above 3,000, but as well as I do have some action in that 1400-1500 region. Again, this 1400-1500 region isn't incredibly diagnostic, as alkanes can get in there, but I don't have a ton of alkane peaks. But I don't have a ton of alkane peaks. So this is, again, very consistent with an aromatic region. But if I had produced acetyl salicylic acid, the big thing I'm missing is I would have an acid. In this case, I did not indeed produce an acid, because instead what I have here is an alcohol. Note, instead of a big, gigantic peak that eliminates all competition in the 3,000 region, I have a still fairly broad peak around 3,300. So if you go ahead and take a look at your spectra, your spectra table, you'll find that this agrees fairly well with an alcohol. So instead of having a species containing an acid, I still have that alcohol present on the salicylic acid. So instead of putting a carbon chain on the acid or on the alcohol, I put it on the acid instead. And so what you're actually seeing here is the spectra for methyl salicylate. So instead of making aspirin, I made oil of wintergreen. So that nice, wonderful fragrance that we're going into in winter season. So it is worth noting that you can generate methyl salicylic acid by treating acetyl salicylic acid by treating salicylic acid with acetic acid. Instead, we treated the system with methanol, which generated that methyl salicylic. So again, methyl salicylate. So something to keep in mind again. Sometimes the big thing here is we're looking for what is absent as well as what might alternatively present. So this molecule really makes use of both skills. So hopefully this is a quick tutorial. Feel free to stop by if you have any questions on how to go ahead and line up these spectra. All right. Until then, good luck, and we will see you in lab.